Thank you very much. So the voice is fine? You can hear my voice, I guess?
Yes, I can hear you very well. Thanks.
Okay, thank you very much for the kind introduction. I'm quite happy to be here as a speaker. I wish to be there as well, but I couldn't make it. I apologize. Today, I'm gonna talk about imaging-based diagnosis in the radiology settings, and I will try to share my experience about the major steps that we are making towards trustworthy AI algorithms. Today, actually, there were many great speakers. They talk about the robust algorithm development, which is definitely one major step towards the trustworthy AI, and also we talk about explanations. Oliver also mentioned that this is also the second, the major steps towards trustworthy AI. And I'm gonna actually today want to focus more in the the step that we can do, which is the need for expert in the loop systems, especially for radiology screening applications. And there may be actually multiple ways to do that. And I'm going to show actually how we can use eye tracking systems in radiology screening settings in real time and in real radiology room, and considering several different applications. I will show mainly lung cancer diagnosis examples, but we'll extend it to other applications, including even non-medical. Ben Locker and also Ender Konukolu mentioned why we should really have robust algorithms. Right? Many of these deep learning algorithms are fragile. So this example from 2019 Science, there is this dermatoscopic image of a benign cyst. So you add little adversarial noise and the decision of the machine learning algorithm changes into malignant. Similarly for rotation, and the decision of the machine learning algorithm is changing. So scientists already realized those the failures, and there is a great number of research coming how to robustify these AI algorithms on these failure cases, right? So another example, this is also one of my favorite nice example from Marilyn's group. They show that with adding adversarial noise with the shape of this heart, actually, even this state-of-the-art segmentation algorithms start, failing. So we definitely need the robust algorithms, and of course it is not enough. So we define actually the roadmap towards trustworthy AI for imaging-based diagnosis system in radiology settings. So we define three major steps to do. One of them is the algorithmic robustness today's speakers talked about, and interpretable machine learning methods is the second one Oliver mentioned, and also other speakers. And today I'll try to show actually how we can actually include radiologists in the loop for this diagnosis. So the human recognition is superior to computers. So the computers, the deep learning algorithms are really great in local tasks that we can combine them, not as a secondary, opinion tool, but let's do something to true collaboration in real radiology room settings, and they can teach each other, something. For algorithmic robustness, I will assume in this talk that actually you have a considerably, reasonably, good, robust algorithm. So we know every day different architectures are coming, but we all realize that actually we should really go beyond accuracy and choose metrics to evaluate those algorithms in different settings using the robustness. And there is this domain generalization codes, and this the Ben Locker mentions about these formal verifications, algorithm auditing, this bias mitigation, and all those things. So this is really great, the start to the robustify your algorithms. Once you are actually having this algorithm set up and necessary, we believe that actually, so there should be in imaging-based diagnosis systems, you should have also explanations. We know that actually this, especially these saliency-based methods are pretty famous, like GradCam, and we know that they have also a lot of failures. But since last year, we see lots of stronger alternative methods are coming about the visual explanation. So this should actually go as a part of this interpretable machine learning. We believe it tells you actually, where your algorithm learns, and it gives you a clue about the model interpretation. But of course, this is not enough. So there should be also radiographical explanations, which is more suited into the true radiological the room experience. So when you go to and see how radiologists are doing lung cancer screening or prostate cancer screening, so they use specific the vocabularies to describe a case. So we want actually very realistic the settings where we should also use those terminologies as a part of AI. And these terminologies, these radiographical explanations, actually the domain specific for different applications. You need to actually define this, and AI can actually learn those parameters as well. So I'm going to actually skip that part too, and multitask learning can be a strong alternative actually doing this. So the expert in the loop systems. So we, as I said, actually are using eye tracking systems in the radiology rooms in real settings try to not really actually disturb the radiologist in the setting. So many of those eye tracking systems in the past, and when we also started, it started in the laboratory environment with a lot of constraint, and in 2D, and the radiologist or your experimenters are actually affected under these settings, and lots of constraints. So first of all, with a lot of computational and engineering effort, we want to do this like the seamlessly integrated into radiology rooms, where usually it is like a darkened environment, and there is a dedicated light source, limited distraction, and what radiologist does is the visual search for each scan for particular examples, and there is also a reporting, and nowadays this is done by this speech to text, the microphone and these recognition systems. So we want to integrate, this system, eye tracking system, into this environment seamlessly. And then at the same time, we want AI to run, and we want this eye tracking system to be an interface between the machine and the human. And we want to actually do this collaborative learning from each other. So as an application, actually, we start with the lung cancer, where it has been known that actually low dose CT scan is actually reducing the lung cancer mortality. And actually, we start with that application, and especially this field is highly visited by Mikaya and many other actual journals. You can see lots of papers in this. The AI is trying to detect and diagnose this lung cancer, the lung tumors. Overly crowded region, and in our case, actually, this is a little bit different because we want to, specifically the help when radiologists are missing tumors, and when also deep learning algorithm produce a lot of false positive that radiologists can help. So they are really great radiologists, but they can miss tumors. For example, here there is a little tiny tumor here. This is very actually easy to, the miss, similar to the normal tissues, but there are also other biases that radiologists may have. In the literature, it says there are more than actually 15, the visual biases for misses and misinterpretations. Two of them actually I highlighted here. One of them is called inattentional bias, very, commonly seen. The other one is satisfaction of search, when the radiologist, let's say, they found one of the tumor, and they may not really look at the other part of the lung, and if there are other tumors there, it can be actually missed. The literature shows actually 30 to 35% of the lung nodules are typically missed during the screening procedure. And there are other problems as well, like overdiagnosis. The human error, actually, particularly in this example, is this satisfaction of search error is there. In the right lung, there is a tumor, and unfortunately, 20 out of 24 radiologists missed this hidden gorilla in the other part of the lung. So there are many biases that deep learning can help. So this is the, how they miss the tumor. And we know that deep learning is also great capturing those small tumors. However, they also produce a lot of, the false positive. So you can see lots of studies just for reducing the false positive cases from CT scans after the first run of, deep learning. So they have strength, they have weaknesses, both of them. And we are, considering that the human expert, in our case, this is radiologist, can help deep learning algorithm to reduce the false positive easily because of the higher level recognition abilities. And the machine learning can also, find, those tiny, the tumor cases, or maybe the tumor, because of the bias, actually, it's not catch. So we can actually combine those things interactively using the eye tracking system as an interface between AI and radiologists. So this is a eye tracking device. Most recently we are using it is not glasses. Several years ago when we started this, actually we started with the glasses. This can be also distracting radiologists, but this version is the stereo camera. Is you just put this below the screen, and it can work in darkened environment as well. Basically, actually, it captures where the radiologists are actually looking at, and produces like these maps, these gaze maps, showing the density of the region, how long they actually stay, and where they look at it. This is our previous setup where the radiologists are using the PAC system in radiology rooms, reading those, the CT scans, and this eye tracking data go to the machine learning algorithm. We call it actually collaborative one, and then it actually produces results to radiologists, and there is this interactive actually learning at both sides. So the good thing here was actually it was the first real radiology room, the settings and in realistic settings. And it was actually 3D. It's not really 2D. So radiologists can do zoom. They can change the contrast, look at other places, other screens, and all kind of actual manipulation can be done. So what this eye tracker device actually produces something like this map. But we want this map. This is the biological attention map, right? So we want this map to be integrated into the AI algorithm. In order to do that, actually, we need to represent the data in a quantitative way. So we actually start to represent this data as a graph. So these gaze patterns, this is a typical gaze patterns from lung cancer, this screening problem from a CT scan. As you can see, this is there are a lot of the gaze patterns. These nodes are shown. So we represented this gaze pattern as a graph where the vertices is actually the fixation regions, like where radiologists look at it. And so the saccades are stored as the edges. Saccade is like this eye movement. So radiologists actually go forth and back in some regions. So they have actually a lot of repeated saccades, edges, and also the regions. So the gaze pattern can be represented like a G here. However, there are so many redundant vertices and edges that we need to minimize this because we want the system to be real time or near real time, and in radiology, real radiology settings, right? So this should be minimized for efficiency reasons, and then this attention of the specific radiologists have specific search patterns, and then you minimize it. And this attention should be used within the AI system. In this way, actually, there is a possibility to personalize the AI system as well, because every radiologist will have different search mechanism, and then you will model their attention and put them into these AI algorithms. And every time they actually work in this system, the system is gonna be, this AI model is gonna be updated and learning the specific search patterns of the the radiologist. For simplicity, let me show the gaze data you have, and then we represent them as a graph. Then we need to remove the vertices because there are so many irrelevant. Actually, is the repeated vertices as well. When the radiologists look at one certain regions, it covers actually many region points. So we need to actually minimize this. And there are a lot of actually redundant saccades, which is this eye movement for the same regions. We need to remove this again for efficiency reason. And once your gaze patterns are specified, actually we put them as the biological attention regions for the CT scan, and then you have the algorithm part. And assume that you have the explainable and the robust algorithm to do your task like segmentation, detection, and also classification like malignant or benign. Nowadays, we are exploring not CNN, but the capsules and transformer-based algorithms because of their the more robustness and the accuracy were higher. In this case, actually, we don't really have any constraint, from the algorithm perspective, or any the highly accurate and robust algorithm can actually replace this part. So there are three portions here. So the gaze analysis, the machine learning part, and the visual attention part. The attention part is coming from different radiologists, and we consider this like a biological, the attention. Like I said, so now you have nodes. These are the fixation and edges, saccades, needs to be sparsified. One example here is that actually, the closest nodes actually representing the same region. So you can do the clustering and then represent only one or a few nodes from every region to represent that, the cluster. This will allow you to have a small number of, attention regions. Similarly, these edges like saccades, there are repeated ones, actually you can find and actually remove them. So mathematically, so our constraints here is this. So you need to have a linear time working algorithm, so near linear time. So clustering algorithm and spectral graph sparsification algorithm can be used here to, to complete this task. I'm gonna skip this part. These are the sparsification. So how we minimize the, the graph. So how we can actually model the attention here, the radiologist attention. For each radiologist, we look at after the sparsification, how many nodes in each cluster. So that tells you actually, the attention mechanism, right? Because they look at certain region in certain densities, and that density is coming from the time. So it's self loop actually. So the time and the location, we multiply them to obtain a one parameter W, which is the radiologist behavior, attentional behavior. That is going to do, the algorithm, the AI algorithm. This is the sparsification algorithm for the toy data set, where we are removing, for example, 60 to 80% of the data. Still the search structure is still there. So you can still actually use this mechanism as an attention mechanism in the AI algorithm. So for the realistic case, so there are 3 radiologists in this example. For the same CT scan, they do the search. So the first row showed the, the dense gaze patterns. And this first radiologist used like almost a little bit more than 2 minutes to finish this search. And after sparsification, we have actually a small number of attention regions to be considered by AI region. The second radiologist have different search style, and the third radiologist is a fresh, the residents finished and spent like more than 5 minutes to finish the same CT scan. So still after sparsification, we have small number of, the points to be considered in AI algorithm. The first radiologist was actually more than 20 years experience. So once the time passes and the experience is also increasing, this search style is changing and they are becoming more faster. And the algorithm, actually, we don't really have any constraint on this. So the only input is coming there is just the attention, the biological attention after sparsification. So once they actually finish in the radiology room, their screening, our system actually shows them actually where they look at it, the covered region like green, and then where they didn't look at it, which is red region. It is not covered, so they didn't really look at that part. So the algorithm is automatically rerun to find tissue at risk for misdiagnosis if there is any. And then radiologists have time to actually change your the report or their system, or pay more attention to those regions. And if there is false positive for in general, so the radiologists are asked to actually click those regions so that the algorithm can be updated later. In our initial works, we were actually doing this like retraining the whole system. Currently, we are actually searching like how we can do this with active learning algorithm without retraining the whole system, but just updating the model per case. So this eye tracking based system for lung cancer, we have shown that the sensitivity is increased after using this lung cancer screening in 3 different centers. We have conducted this, UPenn, NIH, and now in Northwestern. And then we actually start thinking, so can we really use eye tracking for other applications as well? So one of the application is, for example, multi-parametric, the prostate MR screening. So there are, 4 different modalities, and radiologists use multiple screens. So can we also use, the same or similar strategy for this screening? It is of course more difficult because different the modalities, and the fusion operation is really complex in the the cognitive scales. But we have determined actually when they look at when radiologists look at different images like T2 weighted images, and then which ones actually they look most for the diagnostic purposes, and then when they switch into other screen. So we can actually see in this picture like how they actually do that. And since our graphs are directed graphics, we also know for which location when they are not sure in which actually images they go and finalize their screening. So once actually this specification is done also for these 4 different images, so the same system is going back to the AI algorithm for lesion detection and then characterization for prostate. So more lately, actually, we have seen, like today's Ismail Ben Ayat actually mentioned that in medical AI, we are nowhere close to like, the very large scale data annotation and the collection. So we are thinking that how can we use actually eye tracking, because it is integrated into real radiology rooms, right? So when radiologists are using their daily routine, can we collect the data in the behind the screen while they are doing their screening without really having a separate time from them? So we did some the proof of concept studies when the radiologists are looking at the brain tumor images, and silently we collected this data for rough segmentation and labeling using the eye tracking as a seed point. And then actually we collected many data and extended this to another data set, the CT, ultrasound, PET imaging. And as you can see, these are the rough labeling. And we, because of, to make this more efficient, actually, we collected them quite fast. And then all these images can go into the refinement stages, and then radiologists and experts can check, the quality of those labels. So it seems it may be possible to collect large-scale data with eye tracking in routine, the screening time. And before actually finishing, just we are currently actually we have just the initial study here, proof of principle, but we are also exploring as that in radiology room. So there is another technology which is speech recognition, right? So you have this. The microphone, you are recording your reports, radiologists are recording their reports to define the cases. So in addition to eye tracking system, so can we also utilize this technology to improve, the data collection and image analysis? So this, we have shown that actually, this speech recognition can improve the attention regions for the image segmentation in our radiology AI algorithm. This was just the very first work, and hope to explore more in this field. And this is actually my last talk. I want to show that actually we use the same algorithm, but not in eye tracking devices, but with mixed reality glasses. And this time we give this idea to civil engineering problem, where instead of radiologists, we have human inspector, and instead of scans, we have these bridges and the roads, and there are deformities instead of like lung nodules or the pathologists, we have deformities. So can we detect those deformities automatically, real time, and then quantify? And actually we have done this. My student developed these techniques. So real time, we automatically define these regions, and also actually it is possible to define a ROI. And then actually we can do the quantification. I want to show this video to conclude. So especially in difficult regions, in war regions, in places where human experts cannot really go, from a distance, you can just draw an ROI, or you can run the fully automated version. It's gonna find the type of deformities, and then it will do the segmentation for the quantification. This is the crack example in the breach, and this is the SPAL example. And exactly the similar algorithm actually we use. We even the compressed version of what we use in eye tracking, the experiments. So this is also the possible with mixed reality, and hope to integrate this into the virtual reality and augmented reality settings where expert in the loop may be possible too. So to conclude, actually, in image-based diagnostic algorithm, we define 3 major steps to be concluded. One of them is robustness in algorithms, and I totally agree with the previous speakers about the reasoning and those efforts in this field. And interpretability and explainability, the visual and radiographical interpretation should go attached to this radiology screen diagnosis. And we believe that expert in the loop system is increasing the trustworthiness, and there is the complementary power by experts and the AI, and we can utilize them to improve the efficacy of the systems. Our experiments, different experiments in lung cancer, radiation therapy planning, prostate, pancreas, and non-medical imaging experiments all came favorable, and this helps us actually to explore more in this direction. These are my references, and thank you very much for listening.